In this video, we're going to solve 12 hard algebraic proof questions. Let's start. In the first question, it's asking to factorize 2t squared plus 5t plus 2. This can be factorized as 2t plus 1 and t plus 2. In double I, it's saying that t is a positive whole number. Then we need to explain why the expression 2t squared plus 5t plus 2 can never have a value that is a prime number. Since we factorized this expression to 2t plus 1 and t plus 2, this expression we can say that it's a product of two numbers. 2t squared plus 5t plus 2 is always a product of two whole numbers. For any value of t is always a product of two whole numbers. Hence, it can never be a prime number. That's why. In question number 2, it's saying that n is an integer, and we need to prove that the sum of this expression and this expression is always a square number. So let's expand this one. It's going to be half n squared plus half n. And the other one, let's expand these two brackets first. It's going to be half. When we expand these two, it's going to be n squared plus 3n plus 2. Let's distribute the half. So it's going to be half n squared plus 3 over 2n plus 1. So let's add these two together to get half n squared plus half n plus half n squared again plus 3 over 2n plus 1. Let's simplify like terms together. Half n squared and half n squared is n squared. Half n plus 3 over 2n is 2n. And we are left with the plus 1. This expression can be written as n plus 1 all squared, which is a square number. For any bracket that has a power of 2 like this one is always a square number. Whatever value of n we substitute here, we will always get a square number. And that's it for question 2. We are given an arithmetic sequence, and we need to prove that the difference between the squares of any two terms of the sequence is always a multiple of 24. We can't just take any two terms of this sequence with numbers like 13 squared minus 7 squared. Since we are asking for the difference between the squares of any two terms, we can't just take 13 squared minus 7 squared and prove that it's always a multiple of 24. What we need to do is get the nth term of this sequence. For an arithmetic sequence, the nth term has a form a plus n minus 1 times d. That's the form of an arithmetic sequence. We need to get the first term, which is a, and the difference, which is d. So here we have the 7 as dA, and the difference, we always add 6, so the difference is 6. So the arithmetic sequence will have a form of 7 plus n minus 1 times 6, and we need to expand and simplify this 6n minus 6 to get 6n plus 1. So that's the rule for any term in this arithmetic sequence. We need to get two terms of this sequence. So we need a term with n and n plus 1. So the term with just n, we get 6n plus 1. For n plus 1, we can replace n with n plus 1 to get 6n plus 1 plus 1, which is 6n plus 7. Then we need to find the difference between the square of each one. So 6n plus 7 squared minus 6n plus 1 all squared. Let's expand. The first bracket is going to be 36n squared plus 84n plus 49 minus 36n squared plus 12n plus 1. Let's distribute the negative sign. Minus 36n squared minus 12n minus 1. We get, I will continue over here, 36n squared and minus 36n squared, they cancel out. This one is 12n, I forgot to write the n. 84n minus 12n is 72n, and 49 minus 1 is 48. To prove that this is always a multiple of 24, we can take 24 as a common factor. So it's 24 bracket. 72 divided 24 is, let me calculate it, is 3. So we are left with 3n plus 2. That's how we prove that the difference between the squares of any two terms in this arithmetic sequence is always a multiple of 24. We got the nth rule of this sequence to get two terms that are after each other. We use n and n plus 1. We got the rules 6n plus 1 and 6n plus 7. That's two consecutive terms in the sequence. We want the difference between the square of this one and this one. That's what we did over here. Subtract them, expand and simplify. We reached this final expression. To prove that it's always a multiple of 24, we took 24 as a common factor. And that's it. In question number 4, we're given an n is an integer such that n is greater than 1. And we need to prove that n squared minus n is never an odd number. What we can do here is factorizing this expression. Take n as a common factor, we are left with n minus 1. So n minus 1 are two consecutive numbers. Let's say n is 4, so 4 times 3. That's two numbers after each other. For any two numbers that are after each other, one can be odd and the other is even. So we are multiplying an odd number times an even number. We're multiplying odd with even. The product of odd times even is always even. That's how we prove that n squared minus n is never an odd number. We have two numbers that are after each other, n and n minus 1. One could be odd and the other could be even. Doesn't matter their order, even, odd, or odd, even. What's important that their product, when we multiply an odd number times an even number, we always get an even number. That's it. Question number 5. It's saying that the product of two consecutive positive integers is added to the larger of the two integers, and we need to prove that the result is always a square number. So let's break down this statement. The product of two consecutive positive integers. So two consecutive positive integers could be n and n plus 1. Sorry, this is 1. So their product is n plus 1. We multiply both of them together. This product is then added to the larger of the two integers. So we add n plus 1 over here. And we need to prove that this expression over here is always a square number. So let's expand. N squared plus n plus 1. We get n squared plus 2n plus 1. When we factorize this expression, we get n plus 1 all squared, which is always a square number. This is always a square number. And that's it for question number 5. Number 6, the statement says that we need to prove that when the sum of the sum of the squares of any two consecutive odd numbers, when we divide this by 8, the remainder is always 2. So we need to get first two consecutive odd numbers. An odd number have the form 2k plus 1. Why? 2k for any value of k, we get an even number. 2 times k is always even. Plus 1 makes it an odd number. The next odd number we can have is 2k plus 3. So 2k plus 1 and 2k plus 3 are two consecutive odd numbers. Then we need to find what? The sum of the squares. So we need to square each one and add them together. So let's expand and factorize. 4k squared plus 4k plus 1 plus 4k squared plus 12n plus 12k, plus 9. Let's simplify this. 8k squared plus 16k plus 10. Now we need to divide this expression by 8. But how we're going to do this? Instead of dividing, we can try to take 8 as a common factor. However, we can take 8 as a common factor from 10. But what we can do is to rewrite 10 as 8 plus 2. So it's 8k squared plus 16k plus 8 plus 2. From this part over here, we can take 8 as a common factor, and we are left with k squared plus 2k plus 1. And there's a plus 2 outside. That's how we prove that when we divide by 8, there is always a remainder of 2. The presence of plus 2 outside. And that's it for question number 6. In question number 7, we need to prove that if we have 3 consecutive whole numbers, the sum of the square of the smallest number and the square of the largest number, we will add the square of the smallest and the square of the largest. We need to prove that this is always 2 more than twice the middle number, the square of the middle number. So for 3 consecutive whole numbers, we can get n plus 1, and n plus 2. That's 3 consecutive whole numbers. The sum of the square of the smallest one, so it's n squared, and the largest one, n plus 2, all squared. We need to add these together, so let's expand. N squared plus 4n plus 4, we get 2n squared plus 4n plus 4. We need to prove this expression is always 2 more than twice the middle number. So what we can do, instead of playing with this expression, let's multiply the middle term with 2, 2n plus 1, and add 2, since he said that it's always 2 more than twice the square of the middle number. I forgot to add a power 2 over here. So let's expand. We need first to expand the power. So it's n squared plus 2n plus 1 plus 2 outside. Let's continue. So it's 2n squared plus 4n plus 2, which gives us 2n squared plus 4n plus 4. We got the same expression. Hence, we proved the statement. And that's it for question number 7. 8. We need to prove that for any 3 consecutive even numbers, the difference between the square of the largest number and the square of the smallest number is always 8 times the middle number. So we need to get 3 consecutive even numbers. So they are going to be 2n plus 2, and 2n plus 4. These are 3 consecutive even numbers. We need to find the difference between the largest square of the largest one and the smallest one, square of the smallest one. So 2n plus 4 squared minus 2n squared. Let's expand and simplify. We get 4n squared plus 16n plus 16 minus 4n squared. We are left with 16n plus 16. So we need to prove that this is 8 times the middle number. If we take 8 as a common factor, we are left with 2n plus 2. 2n plus 2 is the middle number. Hence, we prove this statement. And that's it for question number 8. In question number 9, we're given a sequence of fractions. The numerator or the numerators of these fractions form a sequence 1, 2, 3, 4, and so on. And the denominators of these fractions also form a sequence of odd numbers 1, 3, 5, 7, and so on. And we are asked to find an expression for the nth term of this sequence. So we can divide this into two parts: the numerator and the denominator. For the numerator, it's 1, 2, 3, 4. We can consider this as an arithmetic sequence with first term a and common difference plus 1. That's the value of d. So we can write it as 1 plus n minus 1 times 1. Let's expand and simplify. 1 plus n minus 1, and we are left with n. So the numerator will have take n, or have a value of n. For the denominator, we have 1, 3, 5, and 7. So same approach. That's a, that's 2. So the common difference here is 2. So it's 1 plus n minus 1 times 2. Let's expand and simplify. 1 plus 2n minus 2, and we are left with 2n minus 1. So the nth term for this sequence can be written as n over 2n minus 1. For any value of n, let's say we substitute n with 1, we get the first term. Let's substitute n with 2, we get the second term, just for checking. For part B of this question, we need to prove that when the square of an odd number is divided by 4, the remainder is 1. The square of an odd number. An odd number can have the form 2n plus 1. So let's square it. It's going to give us 4n squared plus 4n plus 1. So let's divide it by 4, and we should find or get a remainder of 1. Instead of dividing by 4, we can take 4 as a common factor. From the first two terms, we get 4n squared plus n, and there's plus 1 outside. So this is how we prove that when we divide by 4, there is always a remainder of 1, by taking 4 as a common factor from the first two terms and leaving plus 1 outside. And that's it for question number 9. In question number 10, we're given a table of sequence, terms of a sequence, and we need to prove that the sum of any two consecutive terms of this sequence is always a square number. But we need to prove this algebraically. So we need to get the nth rule of this sequence. If we noticed, these terms are always divided by 2. So the denominator is going to be 2. For the numerator, we need to find that pattern. Since this is not an arithmetic sequence, we need to look out for a pattern. If n is 1, the numerator is n. If the numerator is 1 or n is 1, the numerator over here is 1 and 2. Here, if n is 2, the term number is 2, the numerator is 2 and 3. So we can see that if for a term n, this numerator is n and n plus 1. So we can write it as this, n plus 1. and that's the numerator, and that's the nth rule for this sequence. So to get two consecutive terms of this sequence, that's term number 1, and we need to get the next term. So we're going to use n plus 1. So replace this n and this n with n plus 1 to get the next term. n plus 1, n plus 1 plus 1. Let's simplify. We have n plus 1 over 2. Since we're going to add them, so it's plus n plus 1, n plus 2 over 2. We need to prove that this sum is always a square number. How are we going to do this? We can expand. So the expand is n squared plus n plus the other fraction. We can add both fractions directly since both have the same denominator. The expand of the second fraction is n squared plus 3n plus 2. All of this over 2. Let's simplify. N squared, 2n squared plus 4n plus 2 all over 2 to get, if we divide each term by 2, we get n squared plus 2n plus 1. Let's factorize it. It's n plus 1 all squared, which is always a square number. That's how we proved it. And that's it for question number 10. Question number 11, we need to prove that x squared plus x plus 1 is always positive. However, we can't write this as a perfect square, nor factorize it. So we need to use completing square to prove that this expression is always positive. So we're going to complete the square. We take the middle, or half this term. It's 1x, so it's going to be x plus half all squared. We put this minus, it's always like this. We put this minus, and half power 2 is 1 over 4, and there is this plus 1 at the end. So we need to simplify this. Going to be x plus half squared plus 3 over 4. The square bracket is always positive, and this one also is always positive. Hence, we proved that this expression is always positive. And that's it for question number 11. Question number 12 and the last one. We're given a grid that in each row there are 10 numbers. We're given that L, for any number we choose, L is the product of the left and right numbers of the cross. So like here, this is the middle number. L is the product of 34 and 36. And T is the product of the top and bottom numbers. So T here in this case is 25 times 45. And M is the middle number, as we said. We need to prove that when M is 35, L minus T is 99. So L, we said it's the product of 34 and 36. 34 times 36 minus 25 times 45, that's T, the product of top and bottom. 25 times 45. If we calculate this, we get 99. In part B, we are asked that for any number on this grid, we need to prove that L minus T is always 99. So if we notice that if we select a random number like 28 over here, let's call it N. The number on the left is N minus 1. The number on the right is N plus 1. The number on top is N minus 10. And the number on the bottom is N plus 10. So let's rewrite this grid again. N minus 10, N plus 10, N minus 1, and N plus 1. So let's write L minus T. L is the product of these two, N minus 1 and N plus 1. minus t, which is the product of n minus 10 and n plus 10, n minus 10 and n plus 10. Let's expand and simplify. The expand of these two brackets is n squared minus 1, and the expand of these two brackets is n minus 100. Let's distribute the negative sign. That's n squared plus 100. N squared minus n squared, they get cancelled. So we have negative 1 plus 100, which will give us 99. And that's it for question number 12. Thank you for watching.